So we'll wait till 4:05, and then we'll start our session. So the people who have come just now, I'll just post another message. So there are only 3 people attending now. So usually when during week 4 or week 3, we used to have 20-25 people joining in. So I'm not sure if it is the NPTEL content or is just that everyone's workload starts piling up by September, October, and stuff, and those months. Okay, yeah, it's my recording. Yeah, it started. So, do you have doubts from previous week? So I'll assume there is no doubts from previous week or previous assignments. So in this week, um, let me just start now. Yeah, it's still we have 3 minutes to start, but let's just go ahead. Okay. So this week you would have seen a new type of circuit, that is, you have a inverter, right? So let me draw the motor first. This is our motor. So we have 3 windings, 3 phases. Yeah. So this week you would have seen a new type of um, circuit. That's the so there is some ambient noise, but then those are my colleagues discussing something. So I cannot change my location, so you'll have to bear with it. Sorry for that. Okay, so let's take this as phase one. Um, Yellow as phase two, and black is phase three. Yeah. So what this inverter circuit does is that it's again kind of a switching frequency based, um, but here, why is it called an inverter? Because it is changing the polarities between 2 phases. So that is the reason why it is called a inverter. So here we have S1, S2, S3, S4, S5, S6. So all of these switch do have a diode, right? So don't I've not indicated here, but then it is understood. So problems will be asked around the circuit and motor, right? So this is the water circuit. So there are two types of problem given in this assignment. Given that we have the parameters of DC motor, we are also given with RPM, input voltage. Input voltage is to the inverter, right? VG is given. The EMF relationship with omega is given, and then we are asked to find armature voltage and current. So, what is armature voltage as compared to um, brush brushed DC motor or a permanent magnet DC motor that we had covered last week? Here, the armature is at any given point of time. Armature will be two phases activated at once, right? So this will have one resistance. This is one coil. Then this will have another resistance. The voltage across any two phase that is active will be your voltage armature, and the current that goes through the circuit is the uh, current of the armature, right? So we'll be one question. Let's take problem one. Um, so that deals with finding armature current. Let me go to the next page. Okay. So how do we solve this problem? Is that first we need to understand how the circuit is. So let me just draw a simplified version of circuit at the time this these two phases are active. Right. Let me just draw the diagram also. Can I make it a little bigger? Yes. Right. This is through one phase. This is EB and time T. Right. So yeah, the second phase will be. Let's take this to be 180 degrees. This is when it changes the direction is reverse as 180 you would have south pole facing that face. That's the reason that we have to switch uh, the current that flows through it. Yeah. So this is 180, 60. So we'll have another phase that will be rising here. So that will represent using another color, something like this. Then that will have a flat region. That's 1, 2, 3, 4, till here. Right. So then again, this will also follow similar pattern. Right? Then we'll have another phase that is again at an offset of 120. Right. So maybe I have not made it to the scale, uh, but then you can understand from this when we are discussing. So black will be something like this. So now looking at the circuit diagram, how it will look when, let's take Okay, one of these phase will be coming down as NPTEL. Okay, let us just take it this way. Okay, here you can see. Um, yeah. So when two of the phases are active and the third is not, at that time we'll have a circuit diagram that will look like something like this. This is the motor. One phase has no connection to it. So this we can elaborate as resistance that will be our phase 1, then the inductance of it, resistance of phase 2, inductance. So we'll have something like this. So here you can see that during that flat region, we'll have the resistance of both the phases in series. So from there we can write an expression that the voltage across the motor, right, which is your voltage armature, is going to be uh, current, right, IA, or you can say I phase, the current flowing through that phase, two times of our, okay, it's going to be phase 1 plus phase 2. If both the resistance are the same, then you can write two times of it, plus two times of the back EMF is that is generated, because this back EMF is generated from one coil, and then the other back EMF is generated from the other coil, right? So this is our expression. So before we get to this values of VA and yeah, before we get to VA, we have to calculate um, EB, because what we are asked is this one, right? The current through the phase, right? So EB, the expression that is given in the problem, is in this problem is 0.2 times omega, and this is per phase, right? So EB will be equal to 0.2 times 60. The switching frequency, or the since it is a synchronous motor, okay, what does this synchronous mean is that the switching frequency is proportional to omega, right? So this is synchronous, right? So in an asynchronous, it will still be proportional to omega, but there will be some delay, right? So that is how you can think of it. If it is k times of omega, so this will be k times minus some delay. So this will be for an AC motor, which is asynchronous motor. Okay, so here we'll have 12 volts as back EMF. So 2 EB will be 24 volts for two phases. And coming to VA, how do we calculate it? We can normally calculate it based, like, it will be equal to VG when the duty cycle is 1, right? But here the duty cycle is 0.75. So we'll go back to previous lecture where um, for such a circuit where you have two legs, you will have a duty cycle that will be 2D minus 1 times VG. Yeah. So this will be 2 times of 0.75 is 1.5 minus 1, half times 100 volts, that is 50. Yeah. So from these two calculations, we have got all that is required to arrive at current of the phase. Right? So using this value, 50 volts, which is equal to current through the phase 2 times, here the resistance is same uh, across every phase, 0.6 plus 2 times 24 volts, right? So this is going to be 16, no, yeah, 16, no, 16 will 26, sorry, yeah, 26, 26 H times 1.2, right? So the current is nearly 21 something, right? Yeah, 260 by 12, 13 to 20, 10 by 6, 121.33, yeah, 30, yeah, 6, 6. Okay, so this is this type of question, how you solve it. So how we are solving it comes from the knowledge of how the inverter circuit is made. And then there is second type of problem where they change the construction of the motor. They say that a rotor has 4 poles instead of 2 poles. So now, if they are operating at an omega, what will be the switching frequency of your um, Hall, Hall switches, right? So here, can we have a guess like what will happen? Okay, I don't think I'm getting any response. Okay, since we have 4 poles now, let's take the the rotor initially was north south. Now we have north south. So okay, let's take no, okay, let's have an alternative. Okay. How do I construct this? I do not know. Okay, let me have a magnet that's something like this. Okay. Yeah. Based on this, now you can see that at every 60-degree interval, there is a south pole that comes in. So my switching frequency will also double when my poles, number of poles or alternating poles double. So why is that? Is that in one, let's take one phase, um, 2 times, like there is a north pole and a south pole. So I'll have to change my EMF, or the input voltage, that will be a AC wave. I have to make it go faster, because in the negative, um, the south pole will be pushed this way, and the positive, the north, will be pushed this way. So now, if I had a waveform that is something like this for a phase, now I'll have something like this. Yeah. So instead of one cycle, in one cycle, I have to fit entire um, waveform in one, in in one um, quadrant, yeah, in one quadrant of the previous mode of operation. Yeah, so here you'll have um, your output frequency. Let's take if omega was 120, output frequency would have been 20. Now it will be times 2, right? So since it is synchronous, the frequency is equal to omega, right? So this will be 40 hertz, right? Then there we have another question where let's take the rotor as a standard rotor where you have two poles. Now I'm increasing the rotational the rotation speed, angular momentum. Angular uh, velocity. I'm doubling it. So now I'm asked to comment on the back EMF, that is EB, and the frequency of switching. So here again you can guess that since it's a synchronous motor, um, the moment my rotation speed is doubled, it is directly coupled with the frequency of switching. So if it was F1, now it will become 2 times of F1. And since my EMF, now here also we have seen, and expression was given that it is proportional to omega. So this is generally the case, that it will be proportional to omega. So you'll have 2 times of EB. So like this, you may get new questions. These are actually questions that were um, posed previous run of this course back in 2021. So you'll have similar questions, if not the same, where maybe you'd be asked the armature voltage, or maybe this is given, you would be asked input voltage. So questions will be revolving around this knowledge that we have of the inverter circuit. Yeah. So this is pretty much this week's assignment. Is there any questions? Please explain all switch Boolean expression. Okay, let me check the video.
And Hall 3 is low, right? So that can be written as a digital expression.
Yeah, that operation, I think it depends on your waveform. Let me just take the same waveform so that I can explain. My waveform is a little different. Okay. Um, they've given something like this. And the third one starts here. Yellow. Okay. So the switching frequency that they are referring to is for the flat period. Use black. Okay. So here this back EMF rises because it is catching up speed. So when it comes to a constant speed, that is when you would have your um, back EMF to be constant. Okay. Yeah. So here in this period, your switch will be active. Which switch will be active? This is S1 will be active, and here again another phase, right? Where is that phase? Okay, here S3 will be active. So I am commenting on this schematic: S1, S2, S3, S4, right? S3, S4, S5, S6. Okay. Okay. So in this region, you can see that S1 is positive. In this region, S3 is positive. But here you can see in half. Let's take this is time t. After t by 2, you have S. Okay, let me just denote it like this. So this is nothing but the um, black phase that we have, right? So this is active by S6, right? S6 is negative. Hmm? So based on this, on a time series or a time scale, you can have this is positive, this is negative. Yeah, time series. You would have. Can you please show the first part of the presentation? Okay, Balakrishna, I'll do this after um, this particular question. So yeah, you'll have S1 operating for the time period t, okay? And in t by 2 you have S6, that is negative, right? S6 here, right? That will also be for time t. Then after I'm t, here you can see that S3 is positive. So again here S3 will be there. So like this you can construct series of for S1 separately, S2 separately, S3, S4, S5 and S6, right? Here you can see that S3 is going to start from here. Let me use another color, right? S3 as here. Okay, so after t by 2 you will have the red one going in the negative, and one, no, wait, 1, 2, 3, 4, this will start rising. Yeah, it will come here, okay? Blue. Switching between colors are a little difficult. Yeah, so let me make it red also. Hmm. Okay, this is 2 units. Okay, just ignore my mistake. So this is 2 times of what here it is. Okay. So here you can see that S2 is operative, right? So what I mean by negative is not that the switch is having a negative voltage. The switch is just operated, right? Switch will always have 0 or 5 volts or something like this, right? So okay, let me just make a series, right? S1 will be something like this, right? S3 will be something like this. Okay, let me not comment. Yeah,
Just
no up to this one.
just take
Yeah,
the screenshot of that YouTube video and then just draw on
yeah, I
that.
can take a screenshot, but I cannot put it here, right, in my iPad. So that will be difficult. Okay.
Because on every 60 ticket there will be two switches will be operating.
Yes.
Yeah, yeah. On that basis, sir has explained that H1 H2 bar and H1 H3 bar.
Yeah.
There is
Again, you
some
can see, right, S1 and um, S1 and S6 is being operated together in this region, right? That is your 60 degree. Here also you can see this will be nothing but 60 degrees. So every 60 degree you will have two switches that will be on. So here you'll have S4, S5.
Just check
I'm
once
not
that
much.
H1 S3 bar in the three. It means third switch is should be
Their switches different from mine,
okay.
right?
Okay, yeah,
One,
yeah. I
two.
got that. Just check once. Just check once the YouTube video, and that
Yeah,
just
if, I'm
post
checking.
that.
I have another screen. On
Yeah,
that
yeah.
I'm checking. You'll
Just
not
check.
be able to see the
Yeah,
screen.
H1 S3 bar. Just check second switch. Just confirm that how you did that.
Yeah.
That's because third switch is having positive. That's what I.
Um, okay, Pratyush, listen to this argument that I've put, right? My switches is like this: S1, S2, S3, S4, S5, S6. He has it as S1,
Okay,
S2.
1 3 and upper one or 1 3 and I can't even see. 1 2 4 6 1 3 and 5.
1, 3, and 5 are the top legs of three
Okay,
phases.
okay,
2, 4, 6 are the bottom legs of the three phases in the same order,
okay,
respectively. Yeah. But he has given it as S1, S2, right here. The switch 2 is with the third phase, right? If I'm not mistaken. Yeah, he has given it that way. S1, S2, uh, S3, and S4 he has given it differently, and S5 and S6 he has given
one
a
three five
different
is
one.
same. 2 4 6 there will be difference.
Yeah.
Just continue.
Yeah.
Okay, in first 60 degree here uh, there is some mixed of color. I can't able to see.
Even I can't. Let me erase it and put it. It's the same way we have done the H bridge part last week.
Oh, there are four switches.
Yeah, here we have six. Keep the unit also constant. We have blue phase that will be um, yeah, HMI.
If you just start from 30 degree, yeah, correct.
Yeah. Then we have yellow switching from here. Let's see. Let me check once. It should be matching with this one. Yeah. Okay, my scale is different. So let me just make it again. Okay.
Just number the degree, that will be helpful.
Yeah. This is 360. This is 180. There are 6 divisions. Each division will be 30 degrees. Okay. Okay. Yeah. Let me also draw the switches. This one, S5, 6, S2, now S5, S6 are not the same as mine, S3 and S5. Okay. So here's the switching diagram that you see here in the first 30 degrees. S1, S2, S3, S4. Cannot continue. S5, S6. So okay, here for the blue phase, R. Okay. For the blue phase, here you can see in the first 30 degrees, S5 is operational. So this is going to be plus, and then something. Okay, I'm sorry. This will be operational till this, till this phase. Okay. Sorry, 30, 60 degrees. Okay. S5 will be operational till 60 degrees, right? This is one, and then here we have S1 that starts here. So S1 will be active after 30 degrees till this point. Right. Here you can see that this phase, the yellow phase, is also active but negative. It is connected to the negative polarity. S4 is active. Yeah. S4 is active till this duration. Hmm. Yeah. Then after that, yeah, S4 is active. Then we have blue phase in the negative region, blue S6. Oh, have we accounted that? No, right?
Just draw three switches on. That will be enough.
What do you want? Which
Oh,
switches should I be
no,
doing?
no. It means all these is for the positive terminals. That will be okay. After that,
How will it be okay? You should also know that where it is overlapping with S3, S4, S5, and S6, right?
no,
S2,
no, as sir has
S4, and S6.
as sir has done that he has just taken the red, yellow, and blue wherever they have flat EMF. He has considered it positive, and that will be for 180 degree.
Yes,
After
that
on
will
that,
be for 180-degree.
yeah, on that basis,
But
after that he has just bifurcate it at on 60 degrees, and he has just mentioned the switches. On that basis, he has just expressed the Boolean expression.
see, uh, okay, here your negative polarity is also active. So you should also check for which switch is active, even if you take your positive regions only. Still, you will have regions where S5 they'll be at a phase difference, but it's better to visualize at any time which two switches are active, right?
Okay, that's it means it will be
Correct.
okay. It means in spite of that, we are considering negative also.
We have to consider negative, no?
Yeah. That's okay. Sir, okay, correct. One three, he has taken the above one
Yeah,
switches.
he has. See, you will get three set of switches, and that with the phase difference will be other three set of switches.
Yeah, that's it.
Yeah. So
And that should go for 120, 180 degree.
that will go for 180-degree, given that your rotor has one north pole and one south pole.
Yeah, that's why once. But here for a switch one, here 30 degree,
30 degrees. Okay.
30 degree, and here 180 degree, 150 is the difference interval.
150 is coming with the difference, is it? Yeah. So I have done a mistake. Correct.
Here it
So
will be,
the switch will come till this.
yeah, correct,
Yeah.
correct.
Right here. So let me take for this one also. Yeah. So here you can see that SY will also be active. Here two, these two are active. And then switch.
Sorry for interrupting. Just use
Yeah.
that color. It will be so easy.
Then I'll have to switch between a lot of colors.
Okay.
So that will take the entire time.
Okay.
So now you get the logic, right?
Yeah.
So I think you
Logic.
should work it out once. So
No,
once
I
if you,
understood. I understood. That's what I'm saying. That just check once. It means only just for the second.
yeah,
H2. He has mentioned H1 3 bar, H1 H3 bar,
okay.
and third switch is that is on the positive side, positive terminal. That's what I'm getting.
uh, then
Confusing.
it will be in his method of taking the switches, right? He
S2.
has taken all the top ones as 135,
All
then
are
here.
positive. Above one, all are positive. No? Just check once. Over 135 is positive. 462 is negative. First one is correct. First one is correct.
Yeah, the lower one is 2 is here, S here,
What he
2,
has considered one, two, and
S4,
two, three.
S6. He has considered it like this, correct?
Correct. That's what
Yeah.
I'm saying.
So that is the only difference we'll be getting here, no? I mean, the waveform will be the same.
Waveform is same. I mean to say that what he has written the Boolean expression for this switch to
Okay.
H1 H3 bar.
So,
H3 bar. I'm
okay, let me just go through his lecture properly what you are referring. So you can
I'm
mail
just
me
quoting.
once, right? I'll give you my mail ID.
Okay.
You can mail me once because let's just take one more question, or else we'll be um, using time on this. Can you
Okay.
please
Just check
explain how
once.
to solve question 1, question 11, 12, 13 in assignment 7?
Okay.
Unable to solve. Um, I don't think I have access. I have to switch accounts. Um, okay. Balakrishna, you can also mail me. Yeah. Pratish, you had another question
Yeah. Just do that. 11, 12, and 13. That will be good for me also.
in this assignment.
Yeah. Just it means explain that, not to solve.
See, the assignment I have is a different set because we are asked to solve the previous week assignments.
Okay. Similar that.
No, it will not be similar in this order also. If I take 11, 12, 13, the set I have is which of the following are the limitations when considering BLDC
Can
motors?
we share the screen, sir, for the questions?
I don't think can allow that. Let me try
Losing marks
signing
for
out.
assignment, sir. Badly losing marks for assignment.
Okay. Okay. Let me just try switching accounts.
Okay. In previous assignment, there was question that
You mean week 6?
yeah, with six questions
Okay.
to find out that armature ripple current, and another was another question, average current.
Average
What?
current. Yeah.
Yeah, yeah. What's the relationship between them?
Okay. So
Using expression.
yeah, your ripple current will come because of your circuit. You'll have your ripple current something like this, right? This is your my screen is visible, right?
Correct, correct.
Yeah.
Yeah, this
This
is ripple
is
current.
ripple current.
Ripple
Uh,
current.
Given that you don't have in inductance involved, just resistance only, right?
Uh,
So this is your ripple current.
Ripple current.
Then when the switch is not on, your ripple current will be EB by LA because your motor will be still spinning and it will um, give, yeah, sorry, this ripple is when resistance is not considered, right? Sorry. Yeah. So you'll have for the T off time, you'll have EB by LA. So you'll have a spike that looks like a yeah, triangle, right? So when you're asked average of it, um, you'll have to take the area of it, that's your average, or you can just, yeah, if you take the area of it, you'll get it. No, will you get? Mm, you want the average, right?
Yeah, yeah.
Mm. So average expression is I dt divided by integral dt. Right? If you do this, you'll get it. T on, yeah, that's first is the area under this, and then second one is the time, time interval. T on plus T off,
Okay. Uh,
right? So that will give you your,
it means average. We are calculating average on the basis of the off time.
no, you're taking
EB by,
average over one cycle, because after this it's a ripple, right? The
yeah,
ripple
yeah.
will continue and it
Mm.
will be periodic, right?
Okay.
So if you take
Then
for one
above one,
ripple, the
what is that
average
above one?
will be the average over n ripples, because it's periodic.
What is that then? EB upon LA into T of,
Yeah, into T of year, right?
yeah. That's one for.
That is for, that's the slope. EB
Okay,
upon
okay. That's
LA
slope. Okay,
is
okay.
the slope of when the T off period is there, right? So let me
Okay.
just elaborate. I have some space here. Okay.
Okay.
So you'll have a ripple. Let's take something like this. Right? So I'm just indicating different slopes here. Right?
Mm. Mm, I got, yeah, correct. That is that.
And
Correct, correct.
how would the PWM look like? So you
Mm.
have on signal till
Mm.
here,
Mm.
and then you have
No,
off
that is for
signal
T
till
of
here.
time. That's why we are multiplying that. Correct.
Yeah. So this is the slope, right?
Correct.
Di by dt.
As another formula is there, by using just current maximum and minimum, we are calculating both ripple current and average current.
Okay.
I minimum plus I max by 2. That's okay. That by 2. And another one for ripple current, I max minus I minimum is equal to delta I. That is ripple one, that I, how much it goes in there.
Okay. I'll have to see through that. I guess. I don't recall.
Okay.
Give me a second. Yeah. I'm into this. Your weeks. Sorry. This week's 11, 12, 13. Yeah. A BLDC motor with a stator resistance of 0.6, yeah, per phase. Inductance is this much. Drives a robotic arm. The switches of the inverter numbered 1, 3, 5 are the upper devices. 4, 6, 2 are the bottom devices of R, Y, B legs, respectively. Okay. The Hall effect sensors H1, H2, H3 are placed such that forward direction of rotation. Output from H1 has a rising edge, while induced EMF of R phase winding just becomes flat. Okay. Sensor H2, H3 are placed at 120 and 140 respectively from. Okay. This is 120 degrees, right? Okay. 800 RPM. I'll supply a load of 1 Newton meter. What is the motor is energized from 3 phases. Inverter operating from a DC bus of 200. The ratio of magnitudes of flat portion of back EMF waveform. The motor's operating speed is what is this? The ratio of magnitude of flat portion of the back EMF per phase to the operating speed. Okay, this is V by omega, right? Is 0.9. Consider a subinterval of operation where phases R, Y are conducting and generating torque. Determine the Hall switch output during this subinterval. Okay, here they have given two things, that where phases R and Y are conducting and generating torque. So that is, I guess 11th question is pretty much solved, right? Based on this, you can say that which um, Hall sensors will be active.
Similar to that Boolean expression.
Yeah, similar to the Boolean expression. Right? Because see, one more thing is that these recorded lectures are uploaded on YouTube, and we are monitored. So uh, I technically cannot give some answers based on the current assignment.
Okay, sir. At least provide the hints for
Yeah,
the
yeah. So for
questions.
the 11th one, you'll have to check the switching diagram. Right? Based on that, you can say that which Hall sensor will be active. Okay. In question 11, determine the duty ratio of the switch pair that is operated by supplying desired voltage across this one. Okay. Now your torque is given and speed is given. Use the same. This was in previous assignment. Speed torque relation. Where did it go? Yeah, here. Right. Your K is nothing but this one, 0.9. Okay. So this V is VA, armature. But here, armature is not across one phase, it is across any two phase that is active. And you have given inductance and resistance, use those values. Okay. So you can refer to my previous lecture where you will get this relation how to use. Okay. Um, Apart from that, 13, determine the slope of rising current during the PWM operation as mentioned in the question. Again, refer the circuit. Based on that circuit, you find the current that is going through it based on how we have approached the question here. And using that, you can, or not even current, like if you get the voltage um, based on that. Okay, let me just write it here. So we have something like this: resistance of one phase, then inductance, right? Okay. Like this, we'll have another resistance H2. Right? The voltage across this can be calculated like the first problem we encountered. Okay. So this is a voltage across this. Based on that, you can write the equation for this circuit. Right? Let's take I is flowing through this. So voltage VA will be equal to I times of R, I times of R PH1 plus R PH2 phase 2 plus the potential drop across this will be L PH1 di by dt plus they have asked neglect the phase resistance for this calculation. That's what you'll never get a slope. You'll actually get a logarithm exponential function. Okay. Anyway, we'll just put it this way, right? In the end, while calculating, we'll neglect the resistance so that you'll get. So I'm really close to the answer. That's what. Hmm? So let's just neglect this 0 plus LPH1 plus LPH2 times di by dt. Right? With this. So this is the slope. Right? Okay. But you have to calculate VA. That they've asked you to calculate. That how we have calculated before in P1, you have to use that way. Is it fairly clear? Can I share the screen? Okay. Yeah. Is it clear? Is it not clear? Then if it is not clear, let me know. Tell me what is not clear. Okay. I'll assume that it is clear. All right. So you just try this this switching diagram once, as Pratyush has pointed out. So this will give you an idea of how the Hall senses are going to be active, right? So, all right. If there is no question, can we close the session? All right. So I am closing the record. Okay. Pratyush, you have
Yeah,
something to say?
yeah,
Yeah.
yeah. One question was there in this week lecture. Sir has told that for BLDC,
Mm-hmm.
we can't reverse the supply,
Yeah,
just
you
like
cannot.
we did earlier. That will short circuit. Here also we are using diode, correct? In that PMDC also for H bridge we have used a diode, and by changing the path we have just reversed that. But how come we can't use that way for the reversing this code?
Okay. I'm not sure if I understand your question or.
He just mentioned that we can't reverse the direction by simply switching the what you call changing the supply voltage. That's we have done earlier for PMDC. For BLDC, we have to just change the d5 by dt, so that
I'll have to refer then, because see, here also we are switching the frequencies,
yeah, that's what
right? Here also we do. Maybe he would have told in a different context. For that, I'll have to, you can send me a link. So I've sent you my mail ID, right?
yeah,
You
yeah,
can
yeah.
send me that exact point where he has mentioned
Okay,
that,
yeah, yeah,
right? I'll go through it and let you know.
okay, thank you,
Okay.
sir.
Because there can be different way of, he might be indicating something that
Yeah,
must be misunderstood, or maybe I am not aware. Any
yeah,
of
yeah,
that can
yeah,
happen,
that's what
right?
it was somewhat contradicting that earlier. Yes.
Yeah, it is contradicting the way you have explained. It seems contradicting.
Yeah,
So
yeah,
maybe you would have told something
sir has
else.
some concept of that.
Yeah. Okay. Just
Okay,
please
thank
send
you.
me a mail.
Yeah, 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 sure. Also.
Don't hesitate in sending or shooting a mail. Right?
Okay, sure.
It's convenient. Okay.
Thank you.
Any more questions? No.
No, thank you.
All right. Okay. So I'm stopping my recording. Yeah. Thank you.